Okay, well here's a second example from class 18, and I'm going to do the crank slider and do a little velocity analysis in Excel and with SolidWorks, hopefully. Okay, well, from previous analyses, we found that theta 3 in this problem, by the way, this is example 7.3 in Norton. We found that theta 3 was 152.91 degrees. D, which it turns out we don't need, but it is the 126.84 millimeters. So that's the dimension right here. And omega 3 we found was 5.616 radians per second, and that turns out to be clockwise. Counterclockwise, and by the input to this is clockwise. I think in in Excel we ended up using counterclockwise, but then omega ended up being the clockwise. So they just opposite from each other. So it's not a problem. Now the problem in Norton uses alpha 2 as 20 radians per second squared. I have a little bit of an issue with that when trying to solve it in Excel. So I'm going to go ahead and find it as if it's without that acceleration, and that should do the trick, right? So if I use the formula here, I guess I'll write it out, even though you can look it up. You'll see that that's A times alpha 2 cosine theta 2 minus A omega 2 squared sine theta 2 plus B times omega 3 squared sine of theta 3 divided by B cosine of theta 3. This first part right there is going to be 0, all of that, so I don't need to write that out. And then we have 40, I'll put it as a minus 30, but it doesn't matter because this is squared in there. Sine of 60 plus 120, that's B. 5.616 squared, that's omega 3. Sine of 152.91, and all of that divided by 120 cosine of 152.91. And we end up with a alpha of 275.7 radians per second squared. So if we want to get D double dot, that's going to be negative A alpha 2 sine of theta 2 minus A omega 2 squared cosine of theta 2 plus B times alpha 3, so that's the thing we just found, by the way. Sine of theta 3 plus B times omega 3 squared cosine of theta 3. So shove some numbers in there. This first thing right there is going to be 0, and then we proceed with the rest of this. Minus 30 squared cosine of 60 plus 120 times alpha, which was the 275.7, times the sine of 152.91, and I'm running out of room here, plus 120. Omega 3 is 0.5616 squared, and then take the cosine of 152.91. And I end up with a D double dot of negative 6,304 millimeters per second squared. So that's by hand. That's the solution that we get. I also, by the way, this problem is out of the book, so that you could have found the answer in your book when it had 20 radians per second. But we want to try to compare it to Excel. So I'll keep all of this so that I can compare it and flip my screen over. Ta-da! And let's see. Now in Excel, here's where we left off with a velocity example. I'm going to get rid of some things. Let me copy this over to a new page. And I'll just call it acceleration here. And I haven't actually solved this one yet, so we're playing with fire here. So what we had done here, notice that we got the answer of omega and VB by way of equations, taking the numerical difference of the calculated things. What do you call it? The calculated angle and dimension D. We also did it by way of SolidWorks, and we also did it by way of MATLAB. We could keep that all here. I guess it doesn't hurt anything, but we're going to do it in a number of different ways again here. So it kind of almost makes more sense not to have all of them here, but I'll leave them there. So what we're going to do, and maybe I'll just hide them at different times. So let's hide the MATLAB and the SolidWorks. Okay, so we'll hide those even though they're still there. And we're going to take the numerical difference again here, but now we're going to use alpha instead here. So we're going to calculate what alpha 3 is going to be. And then we're also going to take the acceleration of B. And so the numerical difference we'll do just as we had done before. Take, I keep making smiley faces here. There you go, that's a frowny face now. Minus here, divided by parentheses, and take the time right here. Whoops, yep, I got it. Okay, good. And there. And we're left with this as our acceleration, angular acceleration. Cheat, do the same thing here, except we're going to use the velocity here. So this is the second derivative, really, numerically, of and I like to have a little comma there, maybe a little too big. All right. So let's see what happens here. And here is our solution. How did we do? I'm afraid to check. Let's paste it into here and see what our values are. Not too shabby. Okay. So we got 275 and 6,325 compared to 6,304. I'll buy it. Okay. So how about in SolidWorks? I could close this. I don't need to save it. And I don't think I have this open as another thing. Okay, so I'm going to open up my recent. Open recent. And do I have the one that's called example 2? Sure enough. Was it class 16 where I did this? Maybe it was. I think this is it. All right, these are all the proportions. And we have our motion study. And sure enough, we do. Yeah. So let's just modify this and see what happens. So we're going to add to this. We'll do a acceleration and analysis. Acceleration. We're going to get linear acceleration, and let's get the x component, and let's put them right here, and let's put a little vector on there. I was going to make a big old vector. I think that's everything we want to do. Interesting looking plot. Interesting with the little thing going on to it. And maybe, do I want the angular acceleration? Maybe I do. A lot of times I think angular might turn into degrees per second squared. I think so. I don't know if we looked at that previously. We could try it separately. Let's see what happens. It won't kill us. So we would go to acceleration here, subcategory, and we're going to go angular acceleration. And we want the magnitude. And I think that's going to be good enough right here. Let's see what happens. All right, so they are going to give a magnitude, but of course it's taking the square root of it. And yes, sure enough, it's hard to read this, but that does say degrees per second squared. So we would have to do a conversion in that. So actually, while I'm down here, let me go and change that plot. So I'll edit that plot and make it into the Z component. All right, so I think that's going to be okay. Let's see, will it show it now? Actually, I think I need to reveal it, so I need to show plot. Yeah, this isn't a very exciting looking thing right there, right? It looks a lot like a sine wave. I don't think it is quite a sine wave. I think it's actually slightly different. But anyway, let's close these two and let's watch this thing. Let's see, is it going to show us anything cool with these vectors? Yeah, you can watch them go back and forth. Let's zoom out so we can see the magnitudes of them. I don't know if that's cool or not. It's kind of funny how they bounce back and forth from each other. All right. Well, anyway, let me export this. Export? No. The results? No. I think it won't let me. I guess I have to show it in order to export the spreadsheet. Okay. So here is, oh, and they decided to plot it for me. Thanks a lot. So let's put them in here and take a look. So this is, and all the alternate things that we could do. I don't know why I'm bringing this up while I'm doing this. My mind wanders sometimes. Let's see. So anyway, right about here is about the same time step, and you can see that we got 6,426 negative compared to our 6,325. Now, so I guess I could go ahead and calculate this. Well, one thing I could have done as well, I had started to do it, so might as well complete it. Nope, wrong one. I don't know why this thing disappeared. I guess it was over here in the motion study. And we need this guy. We need to show him. I don't think it's able to change what the plot units are. So let me double check here. Did it have any choices in here? Units. Display data not available. Nope. All right. So I'll go to this one and I'll export it as well. And it probably opened it up in a. Yes, it did. And it should have the same time, so I'll only have to grab a hold of the angle right here. So, oh yeah, I need to close this down, come back in here, and really ought to swap these two out, right? Let's see. And that did it put it into scientific notation here. But, oh yeah, and this is in degrees. So we would need to go equals, we could actually do this right here, just go degrees. No, radians, right? Radians. right here. Kaboom, boom, because it's per second squared. Yep, there you go. There's the 275. So these are the two things that we would compare right here. So let me move this over here, and I can go ahead and paste it as values, so I don't have to. Oh, is it not going to let me do that? No, you bastard. Why won't you let me do that? I'll copy you over, and then I'll delete you. So paste his values here. Boom. And then, so I can get rid of both of those columns. So I did that so they would be in the same spot, right? We could do this right here, and we go SolidWorks. And if I want to, just for completeness, paste this in here and then take a look side by side with these other guys, you have very close information on all of them. So we've done a pretty good job of confirming our answer, but we've also kind of understand the approach a little bit better. So that's it for example 2. I didn't do the MATLAB. I think maybe I'll do the MATLAB for both of these in a separate video. So, but of course it isn't all that much different here. The only thing I could have done, that maybe I should have done in this comparison, and once again, it's a lot of lots of comparisons to make. We could unhide these. And one thing that we could do is we could use equations here as well for the entire thing, so that we have the so we have a whole complete set. So let me move this guy over because he's not useful to anything, and let me. I think I only need I only need 2 columns here, and so for this, I'll say the numerical difference and not numerical differentiation, but equations. That's what I want, all equations. So by equations, we're going to find alpha and the acceleration of b, right? So, what? I am copying. Why are you yelling at me? All right. So from my equations, if I were to go and look them up, we don't actually have an alpha 2, so we always kind of need a cell for an alpha 2. So I'll just leave that one out in here, but the equations as we have them set up right here for this would be equal to parentheses, so I'm skipping over the alpha as part of it and saying A, this guy, F4 times, no, I need negative, right? So, oh, I'm so tired. I don't feel like doing it, but that's okay. We'll keep on doing it anyway. F4 times omega 2 squared, F4 squared times sine of theta 2 in radians, make sure. And we're going to add b, which is this guy right here, F4 times omega 3 squared. So, and that's, we'll use the one that's from the equations, and that should be squared, right? Squared times the sine of theta 3, and that should be that guy right here, and close, I believe, and then divide by, and we're going to divide by B, so that's him, and put a F4, and then I'll divide again, and that's my just lazy way of putting both things in the denominator. Cosine of theta 3. And I'll put a box around it and go down there, and there's our answer right there, right? That's the 275, right, that we should have gotten. And now this acceleration right here is going to be equal to negative a F4 times omega 2 squared. So omega, he's F4 as well, squared, and times the cosine of theta 2, which varies, and that's over here, and close that and add in B, F4, times alpha 3. Okay, so that's the thing we just calculated. Boom. And then times the sine of theta 3. And theta 3 is right there. And last thing, add in B again, F4, times omega 3 squared. So omega 3 from equations, make sure we do it from equations, squared, and then times the cosine of theta 3. And if we were very, very, very lucky, we didn't make some stupid mistake. Ta-da! Oh, we were lucky. So there's the answer. And so I can have all of them in one place right here, and maybe I can start graphing them, or taking some percentage differences to try to get a better feel for what the sensitivity was, or what the, I don't know, what the error is. Just try to figure out what the error, try to figure out which one you believe the most. I guess they're all things. It all ends up when we actually try to measure a real thing. That probably has some of the most amount of variation because of the different things that could go into it, and the building and the measuring and that kind of thing. The means of data collection. So how long is my thing? What, 23 minutes? That's a long ass time, man. But we got it done. Sure. I could do a MATLAB one soon and share it. And it'll be interesting. What do we want to show off? Anything at all? I don't know. I can't remember what I've done, so I probably already re-shown things. I've probably already been repeating myself, and people are being too nice to tell me. Because you're a nice group of people, so. So let's see. Well, he's sitting out, so we're gonna bring in the Taylor again. So I probably have shown the Taylor before, but it's such a great guitar. I mean, this is my go-to baby. This is my baby. I love it right here. I remember now, okay.
you.